8 billion years ago, there was no space, no time, nothing. Then, in a fraction of a second, everything that would ever exist began. Not as an explosion, but as the birth of the universe itself, stretching outward from everywhere at once. Every atom you're made of was shaped by that moment. But what actually happened at the very beginning pushes past the edge of what physics can explain. Common intuition of an explosion fails at this starting boundary. A traditional blast flings matter through pre-existing empty space, but the Big Bang created space itself. Space-time did not exist before this moment. Because space itself expanded, the event occurred everywhere at once, leaving the universe with no central point of origin and no outer edge. Time also began with this expansion, meaning there was no prior moment in which the event could sit. No direct observations exist from this dawn. Instead, the story of the origin of the cosmos is a reconstruction built entirely from physical clues. Scientists trace these remnants backward, seeking to understand the state of the universe when all matter and energy was compressed into an area smaller than a subatomic particle. This ultimate limit is the Planck epoch, spanning only the first 10 to the minus 43 seconds of existence. At this threshold, the universe reached a temperature of 1.4 times 10 to the 32 Kelvin, a state so dense that the four fundamental forces of nature were unified into a single superforce. Here, the laws of general relativity and quantum mechanics clash, leaving modern physics unable to calculate what occurred. Without a complete theory of quantum gravity, science cannot definitively describe this boundary. This first fraction of a second remains a realm of theoretical calculation and speculative models, marking the absolute edge of established cosmic history. In 1980, physicist Alan Guth proposed a physical mechanism that resolved the deepest contradictions of the early cosmos. Between 10 to the minus 36 and 10 to the minus 32 seconds after the beginning, a brief and violent expansion occurred, stretching the fabric of space by a factor of at least 10 to the 26. This process, known as cosmic inflation, resolved three fundamental puzzles. The horizon problem, where regions too distant to communicate share identical temperatures. The flatness problem of cosmic geometry, and the total absence of relic magnetic monopoles. By expanding a subatomic patch of space to astronomical scales, almost instantly, inflation smoothed out the contours of the cosmos, explaining why the observable universe appears so homogeneous in every direction. Yet, it did not erase quantum behavior. Before this sudden expansion, subatomic space was a sea of random energy fluctuations. The metric growth caught these tiny quantum fluctuations, microscopic jitters in energy, and stretched them across the expanding void. These subatomic irregularities became macroscopic variations in density, creating the first structural pattern in existence. These variations served as primordial seeds, establishing the gravitational wells where matter would eventually collect. Through Guth's mechanism, the formless dawn acquired a physical blueprint, setting the conditions for everything that followed. The temperature of the expanding cosmos drops to 1 quadrillion Kelvin by a 10 billionth of a second. In this intense heat, quarks, electrons, and their antiparticles flood the void. Matter and antimatter constantly collide, annihilating one another in blinding bursts of radiation. But a tiny, unexplained asymmetry breaks this perfect balance. For every billion particles of antimatter, roughly 1 billion and 1 particles of matter are created. This microscopic excess survives the widespread destruction, leaving a residue of durable matter. By 1 millionth of a second, the temperature plunges to 1 trillion Kelvin. Under these cooler conditions, quarks can no longer exist in isolation. The strong nuclear force binds them in triplets, forming stable hadrons. protons and neutrons now exist as the first permanent building blocks of the physical world, preparing the universe for atomic construction. By 3 minutes, the temperature of the expanding space drops to 1 billion Kelvin. Protons and neutrons collide with enough energy to fuse, initiating primordial nucleosynthesis. For the next 17 minutes, the entire universe acts as a thermonuclear reactor. Protons and neutrons bond to form deuterium, which quickly fuses into helium-4, along with trace amounts of lithium-7. This brief era ends as expansion cools the cosmos further, locking the raw ingredients of the universe into a fixed ratio, 75% hydrogen and 25% helium. In 1948, physicist Ralph Alpher mapped this cosmic chemistry in a paper with George Gamow. Their calculations proved that these elements forged rapidly during these first 20 minutes, establishing the chemical foundation for every star and planet that would eventually form. For 380,000 years, the expanding cosmos remains a dense, glowing plasma of charged particles, trapping photons in a relentless sequence of collisions. Then, as the temperature falls to 3,000 Kelvin, a dramatic transition occurs. Protons and helium nuclei capture free electrons, forming the first neutral atoms. With the scattering obstacles suddenly cleared, light escapes into the void, traveling unhindered for the first time in history. This released radiation persists today as the cosmic microwave background, a faint relic glow filling every corner of the sky. In 1965, radio astronomers Arno Penzias and Robert Wilson accidentally captured this whisper of the early universe. Using a horn antenna at Bell Labs, they detected a persistent, low-frequency hiss that they initially blamed on nesting pigeons. Decades later, space-based observatories turned this static into a precise blueprint of the ancient cosmos. In 1992, the COBE satellite mapped the first microscopic temperature fluctuations within the glow. Subsequent missions, WMAP and Planck, scanned these fluctuations with unprecedented resolution, revealing acoustic peaks that encode the geometry and ingredients of the universe. These tiny ripples are the oldest physical structure visible to science, the primordial fingerprints that would eventually collapse to form the modern cosmos. Following the release of this ancient light, the universe plunged into a dark age lasting hundreds of millions of years. With no stars yet born, the cosmos remained a cold, silent void. Yet gravity was quietly working on the primordial density ripples. The prime architect of this reconstruction was cold dark matter. Because dark matter does not interact with light, it collapsed first, creating massive gravitational wells that served as invisible scaffolding. Hydrogen gas fell into these wells, cooling and condensing until the first metal-free population 3 stars ignited, returning starlight to the cosmos and initiating reionization. In 1970, astronomer Vera Rubin and Kent Ford at Mount Wilson uncovered direct evidence of this unseen mass. Studying the Andromeda Galaxy, they observed outer stars rotating at speeds of nearly 250 kilometers per second, flat rotation curves that defied Keplerian gravity. Luminous matter accounted for only a fraction of the gravitational pull, revealing that up to 90% of cosmic mass is invisible. This dark scaffolding pulled matter into a vast web of filaments, clusters, and voids, matching modern supercomputer simulations and galaxy surveys. In 1998, astronomers studying distant Type 1a, a supernovae, discovered that the expansion of the universe is not slowing down under the pull of gravity, but accelerating. This unexpected cosmic push is driven by an unknown influence named dark energy, which now dominates the cosmos. Yet, the legacy of the Big Bang continues to evolve through the stars themselves. Deep within stellar cores, nuclear fusion hammers light, primordial gases, into heavier elements like carbon, oxygen, and iron. When massive stars explode as supernovae, they scatter these newly forged elements across space, seeding the dust clouds that build planets and make biology possible. Today, cosmic expansion continues, quietly pushing distant galaxies forever out of reach. As our universe grows darker, our window to study its birth is slowly closing. We remain the cosmos looking back at itself, seeking answers before the light fades. Share your thoughts in the comments below.